Alright, so we're going to let A be the set from problem 1-18, and if the sum of these intervals is less than 1, show that the boundary of A does not have measure 0. So let A be the set, and let's remember what it means. So it's the union from I equals 1 to infinity of a collection of intervals, open intervals, AI to BI, such that this collection of intervals contains all the rational numbers in the interval from 0 to 1. And then we're going to let V be the volume of this set, basically. So it's the sum of the lengths. And we're assuming that this is less than 1. All right, cool. So that's what we're starting with. So problem 1-18, if you look back at it, says that the boundary of A is the closed interval from 0 to 1, but you remove all the elements in A. And so that's useful because we want to know something about the boundary of A. All right, so the boundary of A is equal to this. So what we're going to do is, I did this by contradiction. It just seemed the most natural thing to me. Maybe there's a way to do it without contradiction, but this seemed like the most straightforward way. So assume for contradiction that the boundary of A has measure 0. What we're trying to prove is that the boundary of A does not have measure 0, so let's assume that does. So we're going to set epsilon to be the positive number 1 minus V, and let the union from I equals 1 to infinity of Ci di, let this be a cover of the boundary of A such that the total volume, or the sum of di minus Ci, is less than epsilon. And we can do that because the boundary of A is measure 0, so we can contain it, we can cover it by a countable collection of closed intervals of total volume less than epsilon. And that's true for any epsilon, and it's true in particular for epsilon equals 1 minus V. Now, the boundary of A union with A is obviously the interval from 0 to 1, because the boundary of A is everything in this interval which is not in A. So what that means is that if we take all of the intervals AI, BI, this is overall I, and we union that with all the intervals CI, DI, and we consider all those sets overall I, then this must cover this closed interval from 0 to 1, because the AI, BIs cover A, and the CIDIs cover the boundary of A. And when you put that together, you get the entire interval. So this covers this. But if we look at the total volume of these intervals, the sum of the BI minus AI plus the sum of the DI minus CIs, well, what do we know about this? We know that this is, well, the sum of the BI minus AI is less than V. And the sum of the DI minus CI, well, that's less than epsilon, which is equal to 1 minus V. Okay, so this is 1. So we have a cover of an interval of length 1, but the total volume of the intervals that cover that interval from 0 to 1, the sum of all of these lengths of these intervals is less than 1. But then these intervals cannot cover all of this interval from 0 to 1, because if they did, then their total, the total volumes of all these intervals would be at least 1. But it's not. It's strictly less than 1. So this is a contradiction. So I'll write this like this. I sometimes do that. Where did I learn that, actually? I don't know. This is a contradiction, and hence the thing that we assume cannot be true. It cannot be the case that the measure of the boundary of A is 0, so the boundary of A must not have measure 0. All right. Yeah, that's about all there is to this problem. And yeah, I don't really have much else to say, so we're done with this exercise.